Okay, hi guys. It's been a while, but this is Precalculus 3b, which is an introduction to logarithms, which is a new kind of function or operation that is very useful in this unit. So let's get started. So what is a logarithm? And I want to preface everything in this video with in this video we're going to have a lot of equations and stuff, and a lot of it is going to look scary. You guys got this. I know you do. We're going to work through it. You can figure it out. But just to preface this so you don't get jump scared by numbers, right? But a logarithm is basically it's going to complete the cycle of exponential functions. So what do I mean by that? Well, if we have a to the b equals c, this is an exponential, right? It's taking the exponent. It takes a base a and a power b, and it uses that to equal some thing c. So for example, 2 cubed equals 8, right? We are representing the number 8 by a base and a number of times we're multiplying it. So 2 multiplied 3 times. Now we kind of expand on this with roots, right? So usually square roots, but square roots, cube roots, etc., etc. And what a root does is a root is going to take some number and an exponent to our root to figure out the base. And so this would be written as 8 root 3, so the cube root of 8 is equal to 2. And in this case, we are using 8 and 3, the exponent and the final number, to find the base. Whereas here we're using the base and the exponent to find the final number. And so if you're looking at this, you can see, okay, well, what does this have to do with logarithms? Well, in this case, we're taking the base and the exponent. In this case, we're taking the exponent and the final number. And the logarithm is going to take the final number and the base to find the exponent. So if we were completing this cycle, it will be logarithm. It's written log base a. So this number right here is the base. This number right here is the final value, and this is the exponent. So log base 2 of 8. This is basically saying if we have a base 2, then what exponent do we need to raise that base to find the number in parentheses? And so in this case, it's going to be 3. So that's kind of the deal with a logarithm, is it's taking some base and some final number, and we're setting that equal to the exponent that you need to raise the base by to equal the final number. So in this case, a to the b equals c, like we can see up here. So why do we care? What does this mean besides just in the context of like equations in this unit, in the context of how we're going to use it, which we'll get to in a minute? Why do we care about this? Why does this matter? Well, logarithms can be used for many things. One thing that they can be used for, like concepts like logarithms can be used for, is logarithmic scales in models or charts. And so what that basically means is if we see this chart here, this is asking for the views per 4 randomly selected YouTube videos, right? And this one up here we just have a linear scale. It's going to go by 5,000. So 5,000, 10,000, 15,000, 20,000, and 25,000, right? And because of that, this video number 3, we can really see easily it has around 20,000 views, right? Maybe not exactly, but we can really easily see that. But these 3 down here, well, we can't really see how many views they have super accurately. We know it's less than 5,000, right? Because it's the lowest level on the chart, but they're not at all on the same scale, and so we can't really measure them accurately. But if we have a logarithmic scale, we can measure them really accurately. So this is the same graph, but we're going to use a logarithmic scale. And what that means is with every jump up in the y-axis, we're multiplying by 10. You can also think of that as kind of we are moving up one log value by each by each y axis like part, right? So this is log, this has a log value that's equal to 1, right? If we're thinking in terms of log base 10, which is what we're going to see. If, just a quick sidebar, if we have log and that's the entire expression, it doesn't have a base or anything, it's just like log of 100 with no base, the base that's implied if we don't have one is 10. So in this case, it would be 2. But you can see, so that's just a quick side thing for future reference. And you can see we actually, so if we're doing log base 10, right? Log base 10 of 10 is going to be 10 to the first power, which is 1. Log base 10 of 100 is going to be log equals 2. 1,000 log equals 3. 10,000 log equals 4. And 100,000 log equals 5. And so, and this helps because we still can't get exact values. Like number 4, we're not exactly sure where it lies. But we have a much stronger idea of, oh, video number 1 is around 100 views. Video number 2 is around maybe 5,000. Video number 3 is maybe around like 700. And this, we still know this one. Versus, well, we know this one exactly, but we have no idea what these bottom 3 are. Okay, so here's some practice. I already gave you, we're just, in these problems, we're just kind of trying to complete the cycle. So if I'm giving you a function and I'm asking you to use that function to find the logarithm. So pause the video, see if you can figure these out. If you can, that's fine. Just see what you can do. All right, welcome back. So first one, let's just go through these one by one. First one, 5 to the 4th is equal to 625. Find log base 5 of 625. And so we have log, the base of the log function is going to be down here, right? So the base is 5. And we see we also have a base of 5 right here. And so we see that these are matching. And we have a final result in here of 625. And we have a final result here of 625. And so we know that these are matching. And so this log is just going to be equal to the final part that we're missing. It's going to be equal to 4, right? Because we can really just rewrite this log as what is the base, if we have the base of 5 and a number 625, what power do we need to raise the base 5 by to get 625? And that's what we have right here. And now these other ones are kind of similar. So here we have the cube root of 343 is 7. Find log base 7 of 343. Well, here we have the 7s are matching in the bases, right? Because in the square root, we're solving for the base. In the log, the base is down here. We have the final results are matching. They're both in the parentheses of the functions. And so it's just going to be equal to the exponent, which is, again, just the last missing value, 3, right? Because what this is saying is 7 cubed is 343, so the cube root of 343 is 7. Now this one's a little bit different, but you guys got it. So 2 to the 9th is equal to 512. Find x if log base 2 of x is equal to 9. And so here we have the bases are matching again. We got that, right? They're both 2. And we have the exponent in here, is in the exponent spot 9. And this is equal to the exponent, which is also 9. And so the final value is just going to be 512. We're going to fit this in right over here. And if you think about it, this is saying log base 2 of 512 is equal to 9. Well, 2 to the 9th, right? 2 to the 9th is 512. So that seems right. Okay, so this is the slide that's really scary because it looks super complicated and just kind of a big cluster. But you guys got this. We're going to walk through this. So basically, logarithms have several properties that we can get from exponentials because they're related, right? That we can use when we're simplifying them or using them to like solve problems. They're really useful. And so let's say that a to the b is equal to c and a to the d is equal to f, right? Now, if you're remembering your exponential rules, right? If we multiply two exponents with the same base, we're going to add the exponents themselves. So a to the b times a to the d is going to be equal to a to the b plus d. And because of that, what we're really going to do with these log expressions is just kind of move around what the values are, but we're still going to use the same general concept. So we still have base of a, and we still have bases of a everywhere, and we have log base a of cf. Well, we said that c is going to be equal to a times b, and f is going to be equal to a times d, right? And this is going to be equal to log base a of c plus log base a of f. And so what you really got to think of, right, is that each of these log values represents an exponent. And so really b right here is going to be represented by log base a of c. D of here is going to be represented by log base a of f, right, because a to the b is equal to c and a to the d is equal to f. And because by multiplying the numbers you add the exponents, we're going to add the exponents, the log values, when we multiply the numbers inside. And so if you have two numbers multiplied inside of a log, you can split them out into different logs and add them together. And so that's the first one. So let's do an example, right? Log of 16. And we're not going to try to solve this, but this is just for reference, right? Well, 16 can be 4 times 4, right? And so what this could really be is log of 4 times 4, which is equal to log of 4 plus log of 4. So that one's kind of tricky to wrap your mind around, but really when you're trying to learn these logarithm properties, the worst thing you can do is just try to memorize it. So if my explanation didn't make sense, that's fine. I'm not a great teacher. Just try to figure out if you can find some way, whether online or just by kind of looking at stuff down yourself, if you can relate each of these properties to the exponential values. But let's go on to the next property. And that's going to be relatively similar. And if we recall, if I have two exponents with the same base and I divide them, so a to the b over a to the d, it's the same thing as subtracting their exponents. And so that's going to be the same thing in log, if we have some log, right, of quotient, so c over f, it's going to be the same thing as if we split those two logs up and subtract them. And again, we can think of this because each of these log values represents an exponent. So this represents b, this represents d, and this represents multiplying these two values together, right? And so we're really just shifting the perspective on each of these rules. And the last one is going to be if we have some exponent, right, and we raise it to another exponent, we can just multiply the exponents together. So a to the b to the z is equal to a to the b times z, right? And so this is going to be equivalent to if we have some log of exponent c to the z, we can just take that exponent and kind of plop it out here, because we can think of log of a to the c as b. And so for raising that to some power z, right, we can just take z and multiply it by that. And so we can just kind of flop it out there. That's a weird way of describing it, but you get what I'm saying. And again, if you don't, just try to relate them. I'm sorry, I'm not the best teacher. I might leave some like references in the description based on if I can find any good articles, but yeah. Okay, so we have some practice problems here to try out. So look at these, see if you can get a little bit through them at least. They're a little tricky, but I believe in you guys. See if you can just kind of make the logarithm more appropriate to you. Even if you can't solve the problem, see if you can kind of learn something on the way, and then get back to me. All right, so we have the first problem. Simplify 1 plus 5 times log base 2 of a minus log base 2 of 3. And so in here, the trick is we're going to use just a whole lot of log properties. And so the first thing that's sticking out to me is we have 5 times a log. And because of our third log property, right, we know we can kind of just put that 5 up in the exponent here. And so we have log base 2 of a to the 5th minus log base 2 of 3, right? Because we can take whatever number is multiplying that log and just put it in the exponent of the log of the final number itself of a. And now I'm noticing, well, we also have a subtraction of logs here, right? And if we subtract two logs of the same base, that's the same thing as dividing their inputs. And so we can write that as log base 2 of a to the 5th over 3, because we have a to the 5th minus log base 2 of 3. And now you have this 1 here, and you might think this is all you can do. But remember that 1 is log base 2 of 2. And why is that? Well, this is basically saying what number takes base 2, and if you raise it to this number's exponent, it'll equal 2. And 2 to the 1 is 2. And so log base 2 of 2 is going to be the same thing as 1. And so if we take log base 2 of 2 plus log base 2 of a to the 5th over 3, well, this is an addition of logs. And we know from the first rule that that's the same thing as multiplying their inputs. And so we're just going to take this 2, multiply it, and we get log base 2 of 2a to the 5th over 3. And now that was tricky, definitely. It's kind of hard to get intuition for this. So see if you can follow along, rewind if you need to. Yeah. And then we'll look at the second problem. Okay, so the second problem. Find x if 2 to the 2x minus 5 equals 7x. Now this one, if I'm being honest, this is probably the kind of problem that I struggled with the most when I started learning logs, because there isn't a clear way to use logs in here, right? We're not saying log base something. We're not using the actual function, but we're saying we can use logs to find this. And I gave you a hint. Use the third logarithm property, the one that says if we have a constant times some log, we can put the constant in the exponent, right? But it's still tricky. So let's just get into it. So if we have 2 to the 2x minus 5 equals 7x, what we can do is take any log of both sides, because taking the log of both sides, because they're equal, is just like doing any other operation with them. Like if we have 100 equals 100, right? We can take log base 10 of both of these values. Log base 10 of 100 is equal to 2. Log base 10 of 100 is equal to 2. And we get 2 equals 2. And so as long as it's the same base for each logarithm, it's going to stay the same value. And so what we're going to do that here, I just took log base 10 to be efficient because I don't want to write. But if we do that, then we can use the third logarithm rule, right? Because we have 2 to the 2x minus 5 and 7 to the x. And so we can take this 2x minus 5, put it out in the down here multiplying the log, and we can take this x, put it down here multiplying this log. So we get 2x minus 5 times log base 2 is equal to x times log base 7. And then we're just going to solve. And this looks pretty tricky, and it is, but it's just algebra 2. You can treat this stuff like constants. So you guys got it. And so what we're going to do, we can take this out. So 2x times log base 2 minus 5 times log base 2 is equal to x times log base 7. And then we can subtract x times log base 7, right? We're going to get 2x times log base 2 is minus x times log base 7 is equal to 5 times log base 2. And then all these terms on this side have an x in them. So we can just factor out x to get 2 times log base 2 minus log base 7 is equal to 5 times log base 2. And we can divide everything on this side other than the x to get x is equal to 5 times log base 2 minus 2 times log base 2 minus log of 7. And that's roughly equal to negative 6.193. And I think I said base a lot, but remember, it's just in base 10. If I said base, I was just misspeaking. But if we're thinking about this, right, we're going to use logarithms. We're going to take the log of both sides is the first step number 1. And then we're going to use the third logarithm rule to take the x's down. That's the second rule. And then we're just going to solve. And we're going to solve by isolating all the terms with x's and then factoring out that x so we can divide and just get the x by itself. Right? All right, so that's logarithms. It's a very tricky subject, so if you didn't get it, that's fine. I'm going to leave some kind of articles and stuff in the description for help, because I know I'm not the best teacher, but I hope that was at least kind of helpful to you. Regardless, see you in the next video. Thanks.